Hello, I am here to explain the two theories which explains chromatography. The first theory is the plate theory proposed in 1941 by Martin and Sinch. Second is the rate theory proposed in 1956 by Van Demter. Before proceeding to these two theories, let us first remember the basic postulates of chromatography. The first fact is that molecules of the analyte interact with both the stationary and the mobile phase. Thus, its molecules and its movement is influenced by the type of the stationary and the mobile phase. Second, varying molecules behave differently according to the type of the stationary and the mobile phase. The coefficient of distribution are affected by chemical characteristics such as polarity and pH. Now, let us go back to the plate theory. The plate theory is proposed in 1941 by Martin and Sinch. It says that a chromatographic column is divided into segments which were referred to by the scientists to as theoretical plates. This theory can be summed up via an equation which is written as H is equal to L over N, where H is the height equivalent to the plate, L is the length of the column, and N is the number of the theoretical plates. To further understand the plate theory, I have prepared an illustration. Now, let us first look at the first figure. During a chromatographic experiment, there is both a stationary and a mobile phase. Now, the molecules of the analyte are described by these circular shapes. At first, the molecules are present at the stationary phase. However, according to the plate theory, the molecules of the analyte is at equilibrium with both the stationary and the mobile phase. Thus, after some time, the molecules equilibrate and half of the molecule transfers from the stationary to the mobile phase. As such is described by this figure. Now, let us remember that the analyte's molecules are soluble at the mobile phase. Thus, from the first plate, the molecules are transferred to the second plate. Now, let us go back to the fact that the molecules of the analyte is at equilibrium with the stationary and the mobile phase. Hence, the remaining molecules at the first plate equilibrates, and now there are equal number of molecules at the first plate. The same goes for the molecules present at the second plate. Half of the molecules transfers back to the stationary phase and equilibrates, thus there are now equal number of molecules for both phases. At this point, where the molecules could no longer transfer to another plate, or the molecules could no longer be carried by the mobile phase, is called as the state of elution. Now, the state of elution can be determined by certain methods. There are two generally used methods for this. First is the USP method, and second is the half-height method. So, after understanding the plate theory, what are the important implications of this for us? Basically, the plate theory gave way to the proposal of the rate theory, which is now the most commonly used theory or the most accepted theory in chromatography. The rate theory, proposed in 1956 by Van Demter, is basically an improved version of the plate theory. Why do I say an improved version? So, it also accepts the fact that there are segments present in a column, and the molecules of the analyte is at equilibrium at the stationary and the mobile phase. However, there are more factors which are taken account at the rate theory. First, the rate theory describes the processes present in the column more accurately. Second, the rate theory takes account the time it takes for the molecules to achieve equilibrium as a factor in this equation. Third, it says that the bandwidth of the chromatographic process is influenced by the rate of elution. So, let us go to which is called as the bandwidth. Since it is difficult to understand bandwidth theoretically, let us look at this illustration. If we plot the concentration of the analyte versus the distance traveled by it in the stationary phase during the chromatographic process, we can create a table which is similar to this one. The bandwidth in essence is the difference from this point to this point. So, according to the rate theory, there are multiple dispersion processes which influences the bandwidth of the analyte during chromatography. Generally, there are four proposed dispersion processes during the proposal of the rate theory by Van Demter. First is D, which is so called as the eddy diffusion. So let us go back to the stationary phase. We know that the stationary phase, its molecules are not uniformly distributed. So, when the molecules of the analyte passes through it, each of the molecules travels to a different path, which results to a different time it takes for each molecule to reach its destination. Essentially, the difference in the time it takes for each molecule to achieve its destination results to the widening of the bandwidth. The next dispersion process which influences the bandwidth is which is so-called as longitudinal diffusion. So longitudinal diffusion refers to the horizontal transfer or the horizontal diffusion of the molecules. In general, when the molecules are found at the center of the point where you place the analyte, the faster it disperses. And the more it goes afar from the center, the less is the rate of its diffusion is. This is in relation to the number of molecules or the concentration of the molecules found at the center. Since there are more molecules at the center of this point, the rate of its dispersion is also faster, which can be attributed to the Le Chatelier principle. Now, we have explained the first and the second dispersion process. There are two remaining. The third and the fourth are similar to one another. This is because the third and the fourth process is in relation to the chemical characteristic of the analyte in virtue of the stationary and the mobile phase. The third dispersion process is the mass resistance of the analyte due to the stationary phase. And the fourth is the mass resistance of the analyte due to the mobile phase. So, to understand this more easily, it is how the analyte resists the movement through the spaces. So, let us remember the fact that in polarity, non-polar molecules are soluble in non-polar molecules, while polar molecules are also soluble in polar molecules. While in pH, the acid reacts with bases in order to achieve equilibrium. So as the other way around, the bases react with acid to achieve equilibrium. These types of characteristics are important in understanding how the molecules of the analyte resists the movement through the stationary and the mobile phase. The more compatible the analyte is with the type of phase there is present in the chromatographic process, the easier it is for its molecules to move through it. For instance, if the analyte is nonpolar, it is easier for it to move through the mobile phase if the mobile phase is also nonpolar. Hence, usually when a nonpolar analyte is used, a nonpolar mobile phase is used and a polar stationary phase is used. So, we have now discussed the four types of dispersion processes which were used to describe the rate theory. All in all, we have discussed both the rate theory and the plate theory, which are the two theories of the chromatographic processes. These two processes help in understanding how chromatography works and how the molecules are dispersed through the chromatographic column.